Training going. Well, good morning, everybody. Thanks for joining. My name's Itzel Torres, and I'm with 3C Ren. Next slide, please, Russ. I have started the recording of the course, which will be posted on our 3C Ren on-demand page later. We have Russ King with us today, and he will walk us through why energy consultants should learn to do residential HVAC design. Before we get going, I just have a few slides to walk through. Next slide, please. We ask that everybody make sure they are on mute throughout the duration of the course. If you would like to verbally participate, please raise your hand in the participant section and we will call on you to unmute yourself. We encourage you to participate and ask questions through the chat box as well, and Russ will get to your questions. Next slide, please. A few words about who we are. We are the Tri-County Regional Energy Network. We are a collaborative partnership between San Luis Obispo, Santa Barbara, and Ventura counties, working to improve energy efficiency in our region by offering free programs and services for building professionals and households. 3C Ren is funded by ratepayer dollars, which are collected through the Public Goods Charge Fund and the utility bills. Next slide, please. We have the Energy Code Connect program, which serves building professionals by offering trainings and support to make the Energy Code easier to follow. Within the Energy Code Connect program, we offer Energy Code coach service and over-the-phone, online, and in-the-field support for Title 24, Part 6, and Part 11 related questions for both residential and non-residential projects. We also offer online courses and regional forums that are designed to increase overall energy code comprehension and compliance. Next slide, please. We also have our building performance training program, which serves building professionals such as architects, engineers, contractors, and real estate professionals by offering technical and soft skill trainings related to building science principles and high performance buildings. Next slide, please. And we have our home energy savings program, which incentivizes contractors and helps residents save money and make their homes healthier with energy efficient upgrades through incentives and rebates. And with that, I'll pass things over to Russ to get us started with the day. Thank you.
Awesome. Thanks, Itzel. Appreciate it. Good morning, everyone. Glad to have you here with us this morning. It's nice to be here. This class is called Why Energy Consultants Should Learn to Do Residential HVAC Design. And I will be your presenter today. My name is Russ King. I'm a mechanical engineer. I'm the CEO and founder of a company, Coded Energy Inc. We're the developers of Quick Model 3D software. I've been doing HVAC design and Title 24 calculations for 35 years. My first job out of college in 1988 was with Davis Energy Group. My boss was Marshall Hunt. And I did Title 24 calculations on a computer that didn't even have a hard drive. We had to swap floppy disks back and forth. And shortly after that, Marshall taught me how to do manual JS&D load calculations. And I've been doing both of those pretty much ever since. And recently I've focused mostly on HVAC design stuff. Quick Model 3D is an ACA certified manual JS&D load calculation duct design software that my son and I have developed, and we've been marketing that very heavily to HVAC contractors. But one of the things I've learned trying to sell HVAC software to HVAC contractors is no matter how easy you make the software, there's still going to be a very large percentage of those HVAC contractors simply don't want to do load calculations. Either they're ignorant or they're lazy or they're unethical or whatever. they just don't want to. There are a lot who want to and don't have the time, and there are a lot who want to and do, and that's great. I applaud those people, but unfortunately, there's a very large number of contractors who simply don't want to do load calcs, and I've decided that, you know what, we're going to have to do it for them. And so I've been trying to gather as many people as I can together and say, let's all get together, let's do load calculations for HVAC contractors because they're not going to do them. And so we came up with what I think is a very good software. And we have several other programs where we help contractors do it. But it's always occurred to me, and it's always been obvious to me that one of the most obvious groups of people who should be doing load calculations are energy consultants, the people who run the Title 24 energy compliance calculations for homes and demonstrate compliance to the energy code. Because as you will see, the data that's required to do a load calculation and the data that's required to do an energy model is almost exactly the same. And the process is very, very similar. And now there's software that can do both energy codes and uh, load calculations. And there's going to be a class, a very similar class hosted also by 3C Ren on May 30th at 2 p.m. That Nick Brown and I are going to teach together. Nick is an energy consultant, as you probably know, longtime energy consultant, and he's been using software that does both load calculations and Title 24 energy compliance. And we're gonna cover that software. The software's quick model, by the way. But today's class is more generic, more basic, more what's involved with load calculations and why it's a perfect fit for energy consultants. Okay. So I'm going to jump right to the chase and tell you why it's important. First of all, load calcs are easy. All right. There's nothing magical about Manual J. Equipment selection and duct design, however, that takes a lot more experience. A load calculation is a simple calculation. Think of it as a description of a house that describes its heat loss in the winter and its heat gain in the summer. That's all a load calculation is. That is far less than what an energy model is for Title 24 purposes. Excuse me. Um, the hard part is when after you do a load calculation and then you have to pick equipment to match that load. Now you have to start learning about different kinds of equipment and how to read the manufacturer's expanded data tables and stuff like that. And then duct design is complicated too, because what I've learned in my entire career is that an HVAC contractor is going to hate any design that somebody else does. No matter how good that design is, if they didn't do it themselves, they're going to hate it. It's terrible. That's just how it is. So what I typically do is I do a design the way I think it ought to be, and then I tell the contractors that anything you don't like about this design, let me know, and I will modify it within reason. As long as we're getting the right amount of air to the rooms, I can draw a design a million different ways. Okay. Um, so we're going to talk mostly today about load calculation because I think that's obviously that's the first step, and that's the most important step. Is a house needs a load calculation. Now, the 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 software like Energy Pro does a load calculation, but it's a block load. You can do a room by room load, but it's a lot of work. And I really would like to start people to start doing room by room load calculations, and I'll explain why. Then that has everything to do with duct design, good duct design. Okay. So the inputs are pretty much exactly the same as an energy model. You got roof area, wall area, floor area, window area, the kinds of windows, the kinds of floors, all this other stuff. What you don't have in a load calculation that you do have in an energy model are things like efficiencies. The load calculation doesn't care how efficient the equipment is. Okay, it doesn't care how efficient the water heater is. You don't have to put anything in there about water heating, none of that stuff. So it's actually a lot easier to do a load calculation. The only thing that makes a load calculation a little bit more work than an energy model is that you want to do it on a room by room basis. But some of the software out there makes that very easy to do. Okay, so it's not that big of a deal. And like I tell people, if you can do an energy model of a house, an hourly annual energy simulation, you've basically done 8,760 load calculations, okay? Because a load calculation is just one point in time. It's two calculations, one for the summer, one for the winter. The summer one is when it's a certain temperature inside and a certain temperature outside. You're just doing a single calculation for that point in time. And then in the winter, or whatever the other one, I forget I said summer or winter, but one's summer, one's winter, and it's when it's a certain temperature inside and a certain temperature outside. Okay. But an annual energy model starts on, January 1st at 1 a.m. in the morning and it does a calculation for that. And then an hour forward, it does a calculation, hour forward, a calculation. So for an entire year, you'll do 8,760 load calculations. All right. So the point there obviously is that it's basically the same thing. Okay. Most HVAC contractors are not doing load calcs. That is a huge, huge problem. They say they're doing a load calc and they say, oh, 500 square feet per ton, that's a load calculation. That is not a load calculation. They say they're doing load calculation. They might use some really super simple online load calculation that looks at, there's one that looks at aerial photographs of a house and calculates the floor area and does an internet search and all that. Those are really, really crude. Okay. Um, it's been required by code for years to do a load calculation for new construction for sure. In fact, for new construction, the code says you have to do manual J, manual S, and manual D. Okay. For any new system, whether it's an existing house or a new house. The energy code and the green code also say that you should do load calculations for existing homes just for a change out. Okay. And it's just not being enforced. It's not being enforced. Part of it is building departments aren't quite sure what to ask for, and they're not quite sure what to do with it when they ask for it. I actually teach a class for Bayren that trains building departments how to plan check load calculations and duct design. All right, so maybe we should. I think I've actually taught that class for 3C Ren too. So that's a good class if you have building departments that are not enforcing the load calculation stuff. Let's get them trained and get them started enforcing it. So, energy consultants are good at getting information from a set of plans into the software. That's what they do. They're very good at that. That's what is needed to do a load calculation. New software will allow a house model to be used for both an energy model and then you can run it also in a load calculation version of that software. So now it becomes a nice um, if you're doing new construction, you'll do the energy compliance first to determine what the energy features are, and then you take that same model, you run it through the load calculation version of the software, and it does the load calculations. And then when you're comfortable and you get good at it, you can start selecting equipment and start designing ducts. Okay, but I think load calculations are kind of a no-brainer at this point. If you want to get into load calculations and duct design, or sorry, if you want to get into equipment selection and duct design, I encourage you to find a friendly HVAC contractor and work with them and find out what they like to do. I mean, I work with we sell our software all over the country, and I've been coming in contact with HVAC contractors literally in all 50 states. And it's interesting. There's parts of the world where they have never even seen an odd sized duct, a 5-inch, 7-inch, or 9-inch duct. In California, we use those all the time. That's part of the process. There's parts of the country where flex duct isn't even allowed. They've made it illegal in some places. So the point is that the design stuff varies a lot. For example, some contractors like to use the ductboard wedges instead of a sheet metal TY. So you got to kind of find out what personal preference, and there really is a lot of personal preference in duct design. But again, load calculations, no brainer. That's so easy to do for an energy consultant. It could be something you add to your services. What I would like to see, honestly, is energy consultants do the Title 24, do a room by room load calculation, and then offer to sell that file to an HVAC contractor who can then do the equipment selection and duct design, using that file. Okay, so I think that's a reasonable business model. The 2025 code that they just let out the 45-day language for is going to put a bigger emphasis on proper sizing of equipment because there's a huge emphasis on heat pumps. Heat pumps are very susceptible to bad sizing. All right. Furnaces are dumb beasts. They just make flame and heat up the air. They're not that susceptible to oversizing and undersizing. But heat pumps, however, you have to be very, very careful. You need a load calculation on a house to properly size a heat pump. And so there's a much bigger emphasis on that for the 2025 code. Okay, so there you go. There's the reasons why you should do it. Now let's talk about what exactly is involved in doing a load calculation. What does it take to do a load calculation? Okay, so the industry for calculations comes from Air Conditioning Contractors of America. You'll hear them referred to as ACTA or ACCA. It's the largest HVAC trade association in the United States. I just got back from their annual conference in Orlando, Florida. It was a great conference, a lot of good stuff going on. They're a very large and very healthy organization. They publish these ANSI approved manuals. Okay? These are design manuals. They're ANSI approved. That's a big deal to be ANSI approved. That means they go through a very rigorous process. And once they're through the process, they're basically that means that they're um, the quality is good enough that they can be adopted as code language. Okay, and so that's a big deal. And then they're just simply widely recognized as the industry standard for residential HVAC design. Manual J is load calculations. Manual S is equipment selection. Manual D is duct design. I'll talk a little bit more about that. Okay. The California Energy Code requires Manual J and Manual D, and it says or equal. The only thing that's really equal to Manual J is the straight ASHRAE calculations. Like you pull up the ASHRAE Handbook of Fundamentals and you use the math equations for doing heat transfer calculations. As far as a defined process for doing a load calculation on a house, Manual J really is kind of the only game in town. I know that Energy Pro does load calculations. It's an ASHRAE based load calculation, and that's perfectly okay. But the problem is now you gotta do the manual S and manual D, okay, and equipment selection and duct design. So more and more building departments are starting to require it. Every now and then I hear of a new building department that's requiring it, and I'll get a contractor going, oh, the building department of so and so's finally just started asking for load calculations. I've been doing them all this time. But what I tell contractors is they should be doing it anyways. There's no excuse for contractors not to do a load calculation. I've over the years, I've tried asking them nicely. I've tried begging them. I've tried bribing them. Now I've resorted to shaming contractors into doing load calculations. We have a little sticker that we have, and I've got one right here. It says, "Do you even load calc, bro?" And we hand that out at the trade shows and stuff like that. Um, and what I tell them when I teach contractors, what I tell them, my this is my guilt trip that I give them. You've heard the expression that carpenters use: measure twice, cut once, right? If you measure twice, you can cut once, and your board will be the right length. I'm not a professional carpenter. I usually measure once and I often end up having to cut twice. Okay. But hey, I'm not a professional, but that's how I do it. All right. I'm willing to do it. But if you size equipment for a house without doing a load calculation, you're not measuring at all. You're guessing. And that is not professional. An HVAC contractor cannot call themselves a professional if they're sizing equipment without doing a reasonable load calculation. They are simply guessing, and that's not helping anybody. And it's a big problem, and it's going to be an even bigger problem if that continues on with heat pumps. Okay, so contractors need to be doing this. So uh, ACCA, they put out a ton of manuals. The three basic ones are the ones I mentioned: J, which is load calculations; S, which is equipment selection; D, which is duct design. Okay. They also have a whole bunch of other manuals. You may have heard of Manual T for terminal selection. That's how to select a register, a supply register, or a return grill. They have RS as kind of an overview of the design process. Manual H is specifically on heat pumps. Their newest manual is Manual LLH, all right, for low load homes. Houses are getting so efficient, like with passive house and stuff like that. The house building shell is so efficient that you can heat and cool this really large house with this little teeny tiny heating and cooling system. And there's some special considerations that go into that, how much air changes you need and those sorts of things. And Manual LLH is all about that. And then ACCA also has these great standards and checklists. These are mostly of these are free PDF downloads. Their QI standards, quality installation standards, is really good. There's a quality maintenance standard that's really good. So I encourage you to check those out too. And then their website, of course, is acca.org. So let's get really, really basic, and we're going to talk about what exactly is a load calculation and what does it entail. So, all right, so we're going to cover some really, really basic thermodynamics. First of all, let's define a BTU. And it always helps to think of loads as the movement of heat, whether the heat is coming into the house in the summertime or the heat is leaving the house in the wintertime. What we're talking about is heat, and the way we measure heat is in BTUs. All right, British thermal unit. So a BTU is about the same amount of heat that's stored in a wooden match. So if you take a match, you strike it, you let it burn all the way down, you've just released about a BTU of heat. Okay, so BTUs equals kitchen matches. All right, but we're talking about movement of heat, and when we talk about movement of heat, we have to talk about a rate of heat movement, and what that means is BTUs per period of time, and so we talk about BTUs per hour. Okay, so if I take a match and strike it and let it burn all the way down and release it, I strike another, let it burn, strike another, let it burn. If I do that 1,000 times in an hour, I've released 1,000 BTUs per hour. I've put 1,000 BTUs per hour into the air. Okay. Now, when we calculate heating and cooling on a house, we're going to calculate it in BTUs per hour, but we're going to have to look at all aspects of the house. How is that heat getting from the outside to the inside? All right. And as you probably know, the second law of thermodynamics states that heat always moves from a warmer area to a cooler area, where there's more BTUs to where there's less BTUs. All right. And in the summer, the BTUs are more concentrated outside of the house, so they're naturally trying to come into the house. And as they're coming in, if we want the indoor temperature to stay the same and not rise, we want to stay a nice comfortable 75 degrees. If we want it to not rise, we have to remove those BTUs at the same rate that they're coming in. Well, we remove those with a piece of equipment, an air conditioner, but we have to calculate how many are coming in so that we can size that piece of equipment. Okay. So in the summer, BTUs are on the outside. When we call something a cooling load, what we're doing is we're calculating how many BTUs per hour are coming into the house so that we can then size an air conditioner to remove those BTUs at least the same rate to maintain that comfortable temperature. All right. So when we cool something, we're removing BTUs. We're not putting coldness into a house. We are removing BTUs. So when you say an air conditioner has a cooling capacity of about 24,000 BTUs per hour, that basically means it can remove 24,000 kitchen matches worth of heat from the house in 1 hour. Okay. And so that's, we can calculate the capacity of the equipment, but in order to probably size that equipment, we have to calculate how much heat's coming in to the house, the cooling load. And then basically the opposite is true in heating. The BTUs are more concentrated inside the house, so they're trying to leave. All right, they're trying to escape. And if we just let them escape, the temperature is going to drop inside the house. But we want to keep it at a nice, comfortable 68 degrees, which is California thing. The rest of the country is 70. For some reason, California has decided to use 68 as their indoor winter design temperature, and it is what it is. Don't worry too much about the design temperatures, but what they do is they set a delta T. But anyways, we're trying to keep it nice and comfortable inside. The heat is escaping. We can calculate the rate at which the heat is escaping so that we can size a piece of equipment to replace that heat that is escaping and keep the house comfortable. So when we heat something, we're putting BTUs into it. We're adding BTUs to a space when we heat something up. So you look at a furnace, 30,000, 40,000, 50,000, 120,000 BTU per hour furnace means it can add 30,000 kitchen matches worth of heat to the house in an hour. Okay. So so load is what the house needs. Capacity is what the equipment gives us. And good equipment sizing is an art to matching the load, or sorry, matching the capacity to the load. Think of load as demand. That's what the house needs. Capacity is supply. That's what the equipment gives us. We can calculate the load. We can determine design conditions of pieces of equipment, but then we have to pick the piece of equipment that's not too big and not too small. Now, a lot of people don't realize that you can be too big. And I will tell you from my experience, oversizing equipment will cause more comfort complaints than undersizing equipment. Okay. I have graphs and data to prove that fact. So to maintain a constant temperature inside the house, the rate of heat coming in must equal the rate of heat going out. Okay. Pretty straightforward. And I got a little ahead of my slides. I apologize. So I'm going to repeat myself here. The capacity of the heating or cooling equipment is the output of the equipment. It's how much heat can a heater give us and how much heat can an air conditioner remove. That's the capacity. Think of that as supply. And then the load of the house is what the house needs. The house needs a certain amount of heating to stay warm, and a house needs a certain amount of cooling to stay cool. All right. And the load of house, think of that as the demand. So good equipment sizing is the ability to match the equipment supply to the house's demand. And again, you can be oversized. Now, design conditions. This is the one place where especially HVAC contractors like to monkey around with the load calculations. So design conditions are the specific indoor and outdoor temperatures at which the loads are calculated. Remember I said there's only two of them. There's one in the summer and there's one in the winter. Okay? And the indoor temperatures are set by code. In California, in the winter, the indoor temperature is 68. Think of that as your thermostat set point, 68 degrees. In the summer, it's 75. Okay. So those are your indoor temperatures. Your outdoor temperatures come from tables. You look up the city that you're doing the design for, and it will give you an outdoor design temperature for the summer and an outdoor design temperature for the winter. Again, that's where HVAC contractors like to monkey around with those numbers because they look at them and they go, "Whoa, wait a second. Summer outdoor temperature of 98? Oh no, man, it gets 105 around here. I'm going to use 105." That's not how to use those temperatures. That first of all, that's against code. Okay, and that's not how you should think of those temperatures as I'm going to design to a really hot temperature than it last summer. Okay, that's not how you think of those temperatures. Do what the code says, and you'll be fine. Okay, do what the code says. Use the indoor and outdoor temperatures that code says, and you will be fine. You don't have to worry about those numbers. All right. So don't design to the very worst temperature expected because then you're going to oversize the equipment. And as like I said a minute ago, oversized equipment will cause more comfort complaints than undersized equipment. Plus, it's going to use more energy. Plus, it's going to shorten the life of the equipment. Okay. There's so many reasons not to oversize equipment. We should be looking for excuses to undersize equipment. But it's human nature to say, oh, here's a load calc. Oh, this piece of equipment, it just barely meets it. Oh gosh, I think I'll go to the next size up. That's just human nature. We should be looking for reasons to do the opposite. We should be looking for reasons to go down a size if we possibly can. Okay. Let's see. I got some questions here. I think I need to catch up on. Okay. Danica, you want that sticker? Okay, we'll get you one. um, is the HVAC contractor incentivized recommending larger capacity because it's more expensive? I would say generally speaking, yes. But their main reason for doing it is because they're chicken. They're afraid to put in smaller equipment. They're afraid that something's going to happen. And what's going on is that they oversize equipment and then they'll undersize the ducts. If they don't do a good design, they oversize equipment and undersize ducts, and then there's a problem. And they're like, oh gosh, well, maybe we undersize the equipment. Let's go up a size bigger on the next house. And then the problem just gets worse. But if they properly size the equipment and properly size the ducts, it'll work fine. It's just they don't take the time to do that. So they don't understand. But there is some incentive to oversize equipment in terms of cost, but it's more an issue of they're just afraid to undersize, and so they're rounding up basically. Steve asked, where do the outdoor temperatures come from? ASHRAE, yes, it's all in the ASHRAE. Well, it's ASHRAE and NOAA, the Atmospheric Administration, gets together and ASHRAE mines this data and then does some statistical analysis on it and recommends that certain temperatures be used for certain cities. And I think they're in the process of reevaluating it because, as you know, global warming and all that stuff, design temperatures probably should go up on the summer in some parts of the country at least. But again, I have a blog article about why a degree here or there is not that big of a deal. There's other things in the load calculation that have a much bigger impact that you should be way more worried about than just what indoor temperature and outdoor temperature you use, plus or minus a few degrees. Okay. All right. So the thing to realize is that the system needs to work on mild days. All right. In fact, when you pick a temperature, an outdoor, let's say a summer outdoor design temperature here in Sacramento, the outdoor design temperature is 98 degrees. Okay. That temperature is called the 1 percentile temperature. What that means is it's only hotter than that 1% of the time. Okay. So we design our air conditioner to work when it's 98 degrees. The problem is it's less than 98 degrees 99% of the time. All right. And so when it's much less than, let's say when it's 88 degrees outside and your air conditioner kicks on, your air conditioner is by definition oversized. And then if it's oversized for 98, it's going to be way oversized for 88. And then you get all those oversizing problems that I talked about. And we're in a dry climate. If you're in a humid climate, oversizing is even worse because it doesn't remove as much moisture from the air. You get humidity issues. We can actually create humidity issues in a dry climate when your equipment's way oversized. Um, so if we design to really bad condition, the equipment will be oversized most of the season. Now the good news is you're starting to see a lot more variable speed equipment, and that's equipment that has a high speed that they run at, but it can throttle down to low speeds. All right. That has saved a lot of contractors because they way oversize the equipment, but it's able to run on a lower speed and not have all the oversize issue. But the problem is it always runs on a lower speed. They've oversized the equipment for no reason. An oversized variable speed of equipment is also known as the world's most expensive single speed piece of equipment. Okay, it's not a good idea. If you do a load calculation, size your maximum, and then manual S, the equipment selection, allows you to oversize a certain percent compared to your load, but there's maximums. For variable speed equipment, you can oversize by 30% because it has that ability to throttle down. But for single speed equipment, you're only supposed to oversize by 15%. That's not a very big extra margin there, but you'll see contractors exceed that by a lot. I've seen single speed equipment that was sized for twice what the cooling load is. Okay. That's that's a recipe for disaster. All right. So the design conditions are based on specific indoor and outdoor temperatures. The difference between the indoor design temperature and the outdoor design temperature for the summer and winter is called the delta T. And that's what drives the heat transfer. Okay. There's three kinds of heat transfer: convection, conduction, radiation. Convection is driven by delta T. Conduction is driven by delta T. Radiation is regardless of delta T. Okay. The same amount of heat passes through a window in the wintertime as it does in the summertime, except for the angle of the sun, but still the same amount of heat. It doesn't matter what the delta T is, solar gains will still happen. Okay. So, but the two main ones, well, the other ones, convection and conduction, those are very much driven by the delta T. Okay. So, load calculations are critical to properly sizing heating and cooling equipment. For air conditioners, if you undersize the air conditioner, if you put an air conditioner that's one size too small, it's only not going to work on very hot days. Okay. And by not work, I mean, it's not going to hold the set temperature. So it might creep up from 75 to 76 to 77 to 78, maybe a little more if it's really undersized, but that's only going to happen on those really, really hot days. The rest of the year, it's going to work great. It's going to work really well on those mild days. But when you oversize equipment, you're going to have oversizing problems on the vast majority of the time. Okay. When you oversize equipment, it exacerbates stratification because you're blowing really cold air into the house for a very short period of time, and it doesn't mix well. And it settles to the ground, it settles to the first floor, and it doesn't have the time. The equipment doesn't run long enough for the house to mix, for the thermostat to get a good sense of what the average temperature in the house is. Okay. Those short cycling is really, really bad for comfort. Um, it causes uneven temperature distribution. Plus, running a bigger piece of equipment to do the same job uses more energy. Okay, so your bills are going to go up. Then, to make things even worse, that short cycling on, off, on, off, on, off causes the equipment to fail sooner. Okay. So a lot of problems associated with oversizing. I have some data logger data that I've used in some of my training that shows exactly what I'm talking about. Short cycling causes rooms to start to drift away from the thermostat set point. Okay. So again, we should be looking for excuses to put in a smaller piece of equipment, not excuses to put in a bigger piece of equipment. So load calculations, again, for heaters, undersizing will cause a house not to heat properly on a really cold day. All right. It won't cause a health and safety issue. All right. But if you oversize, you could potentially put more strain on the grid. All right. You've got this really large piece of equipment cycling on and off, higher energy bills. The equipment may fail sooner than on a very cold day. That's a health and safety issue, but undersizing doesn't have those problems. Okay. Question. What is your Jenna is asking? What is your theory on why designers oversize? Complaints of thermal comfort? Yeah, it's because they're not doing a load calculation. It's kind of like, here's my analogy. It's kind of like it's kind of like sizing a tuxedo on somebody based purely on their weight. Okay, like they don't tell you how tall they are. They just say, I weigh this much. Now make a tuxedo for me. Well, what are you going to do? You're going to make it big, right? You're going to oversize, and that's pretty much it. And the problem is they're not measuring. That's the thing, is they're not measuring. They're guessing, and when you guess, it's human nature to guess big. They don't realize that oversizing causes all these problems. Very few contractors have even been trained or come to the realization that oversizing equipment is causing most of these comfort problems that they're blaming on undersizing. Okay, and it's a shame. It's a shame. So welcome to my world. I spend a lot of time trying to train contractors why oversizing causes all these problems and why they should be doing load calculations. So undersized equipment will work fine on milder days, which is most of the time. Oversized equipment will perform worse on milder days, which is most of the time. Oversized equipment can cause more comfort complaints. I say will. Oversized equipment will cause more comfort complaints than undersized equipment. All right. So don't be afraid to not bump it up the size. Okay. The negative, well, but let me qualify that. This all goes with good duct design. If you screw up the duct design, your very perfectly sized equipment may have some issues, and they may blame that on undersizing. Okay, so the negative impacts of both oversized and undersized equipment can be reduced with good duct design. All right, good duct design, which means good system airflow, so that you're getting good airflow, CFM per ton, good overall airflow through the entire system. Okay, that's good system airflow, but then that air is going where it needs to go. That's manual D. That's getting the air to go to the rooms at the right rate. Okay, if you do those, then a properly sized equipment, which might seem a lot smaller than people might think, will work just fine. Just fine. Okay. All right. Historically, the most common method of equipment sizing was rules of thumb, the good old 500 square feet per ton. I've seen that 1,000 times, at least 1,000 times. And then they do trial and error. They go, well, let's try it at 500 square feet per ton. Oh, they're having problems. Oh, let's bump it up half a ton. I guess we were too small. But they never stop to say, oh, well, maybe it's the airflow. Maybe it's the short cycling problem. Maybe it's stratification caused by oversized equipment. They just say, oh, no, it must be, let's just put it in bigger. They just have this bigger is better attitude. All right. And oversized equipment is almost always goes hand in hand with undersized ducts. It's the same problem. They're not doing design. They're not doing good design. They're not doing load calculation. You would think that they would say, well, I'm not sure about how big of a duct I should put in this room, so let's put in a bigger duct than we need. They don't. They just say, oh, it's a better one, it gets a 6. Oh, it's this, it gets an 8. Oh, it's one of those, it gets an 8. And they just use rule of thumbs, and that just causes problems. Okay. So another important thing related to duct sizing is you're controlling the temperature of the entire house. You've got an entire house, and you're controlling the temperature in all those rooms with one location. That's where the thermostat is. Okay. That one location where the thermostat is usually in a hallway, usually close to the return grill. All right. If that one location is not the same temperature as the other rooms, it's going to it doesn't care. It doesn't know what's going on. The thermostat's happy. The thermostat's all cozy and warm and toasty or cool, whatever. And it doesn't care what's going on in those other rooms. It shuts off when it needs to shut off. When it senses the thermostat, the temperature is the right thing, it's going to shut off the system. So how do we make sure that the temperature at the thermostat is at least within a couple degrees of the temperature in the farthest room away? And the way you do that is to make sure the system runs for a long time. Make sure that air cycles around. And if you undersize equipment, that does not happen. It shuts off too soon. If equipment is properly sized, theoretically, if equipment is properly sized, when the outdoor temperature is at or above the design temperature, the system should run continuously. It turns out it doesn't. It turns out that manual J is safe. And it actually I don't want to say it oversizes equipment, but it's manual J is safe. Manual J assumes worst case conditions, which rarely occur. Okay. So it's always going to be safe. And then by taking a few extra little, you know, precautions, closing drapes, don't flush your house out with hot air on a hot day and let all the thermal mass get hot and then try to keep up, stuff like that. So good duct design is important to making sure the temperature is even throughout the house, but so is equipment sizing is very important to that. All right. So sizing ducts to deliver the proper airflow to each room or register. So target airflows, how much air a room needs is based on that room's load. It's a simple formula. It's a very simple formula. If a room is 10% of the cooling load, it needs 10% of the air. So I like 2.5 tons because it's a nice round number. 2.5 tons is going to move about 1,000 CFM. Okay, 400 CFM per ton. 2.5 tons is 1,000 CFM. If a room is 10% of the total cooling load, it needs 10% of the airflow, which means it needs 100 CFM. It's that simple. All right. But you don't know that number unless you know that load, the room by room load calculation. You take the room load divided by the total load to get what's called the factor, the cooling factor, and you multiply that times the total airflow, and there you go. I think I have some slides on that actually. So the problem though is when you start undersizing all of the ducts, design. That's one of the biggest problems is when they don't do a good design, they don't they don't size the entire duct system to handle all of the airflow. Okay. They just throw some ducts in because there's a certain number of rooms, but they don't stop and say, well, all these ducts I just put into these rooms, is that enough ducts to handle all the airflow that I want to move when the system's running? And it's usually not. That's why ducts get undersized. And they also have a very bad habit of undersizing the return ducts, which is like the bottleneck in the entire system. And when you do that, when you reduce the overall system airflow, it's a double whammy. And by that I mean not only it's pretty obvious if you reduce airflow, you're going to reduce the cooling capacity, right? If you reduce the airflow, the capacity is going to be less. But not only does the capacity go down, the ability to cool, the efficiency goes down. It actually affects the SEER rating of an air conditioner when you start choking off the airflow. All right. So good duct design is very important. Undersizing one or two ducts relative to the rest of the house will cause poor air balance. And what that does is it makes those rooms, if you undersize one or two ducts, those rooms will get less airflow than they need relative to the rest of the house. So they will be under conditioned. So they'll be hotter in the summer and colder in the winter. Okay. So that's uneven temperature distribution. But if you have good overall airflow, if all of your ducts is happy and you have good equipment sizing, it hides a lot of that stuff. You won't notice those things. So I like to say good airflow and good equipment sizing forgives a lot of sins. Otherwise, if you undersize a duct here or there and you have good airflow and long run cycles, you may never even know that's an issue. Okay. But if you start choking off the airflow, pretty soon those rooms that aren't getting enough air, they'll become an issue. They'll become more noticeable. All right. So this is made even worse by low overall airflow. So equipment cannot be properly sized unless you can determine the capacity of that equipment at design conditions. That's what manual S is all about. That's one of the main things, because you say this 2-ton air conditioner is going to give you, and everyone will say, well, a ton's 12,000 BTUs, so a 2-ton air conditioner should give you 24,000 BTUs of cooling. It's not that simple, unfortunately. That same 2-ton air conditioner in San Luis Obispo is going to give you a very, very different amount of cooling than a 2-ton air conditioner, the exact same 2-ton air conditioner in Palm Springs. All right. So the ability for an air conditioner to cool, its cooling capacity depends on design conditions. So what is that outdoor temperature that it has to operate at? All right. So you need to be able to determine that. That's what manual S is. So that's the ability to go into the manufacturers, what they call the expanded data tables, and say this piece of equipment will give us this much cooling under these conditions. And it includes outdoor temperature, humidity, indoor humidity, airflow, and stuff like that. Okay. So you need to be able to do that. That's manual S. And then manual S will also say, if this is your load and here's your capacity, make sure your capacity is not too big or too small. So manual S has those ranges, but it also goes into a lot of detail about how to determine that actual design capacity. Okay. Steve, hi Steve, by the way. What do you do if your cooling load is 10% and your heating load is 5% of the total airflow? You pick the higher of the two. Yep, great question. You pick the higher of the two. So if in the winter a room needs 100 CFM and in the summer that room needs 120 CFM, you size the duct for the higher of the two. You size it for the 120. Now what that does is it actually makes your entire duct system bigger than it needs to be. If you pick the worst case, let's say you're designing for 1,000 CFM, and some rooms have a higher cooling and some have a higher heating, um, you may be designing a system for 1,100 CFM, but the system will never see more than 1,000 CFM. But that's because you want that worst case airflow to be able to go to those rooms. And then everyone is like, oh, well, do you have to adjust? Do you have to open registers in the summer and close them in the winter and blah, blah, blah? No, you don't. If you, like I said, if you do a good design, you have good airflow, good equipment sizing, nice long run times, those sorts of things become a non-issue. And it's good because you're slightly oversizing the equipment. It is not a big deal to oversize ducts. Okay. And I will even go so far as to say on the return side, you cannot have a return duct that's too big. Okay. I'll say that again. On the return side, you cannot have a return duct that's too big. Okay. On the supply side, maybe there's some arguments that when your ducts start getting too big, you have more surface area and more heat transfer. But if your ducts are inside conditioned space, it's not an issue. Okay. And if you have good overall airflow, everything works better. Okay. All right. Ducts cannot be properly sized unless you know how to distribute the air. In order to do that, you need room by room load calcs. That's why I'm a big stickler, or that's why I really, really insist that if you're going to do a load calculation, you may as well do room by room. It's not that much more work in the new software. Okay. All right. So let's talk about the big picture. So now we talked about why it's important to do a load calculation. Now let's talk about what does it entail. Okay. What does it entail? So there's 4 basic steps. The first step is to collect the information about the house. So you're going to need a set of plans. You're going to need all the energy features. You're going to need the design location. You're going to have to know the kinds of windows and all that other stuff. You don't need to know anything about the water heating. You don't need to know anything about the solar panels. You don't need to know a lot of the stuff that you need for Title 24. It's really just heating and cooling. Okay. So in some sense, it's easier. If you're doing new construction, you got your architectural plans, you got your Title 24 report. That's all you need. That's all you need. Okay. But for existing homes, I do a lot of existing homes, and I encourage people to do existing homes. That's kind of my big push. You may have to go out to the house and collect the information in the field. All right. And back in the day, we used to, and I've trained a lot of HERS raters to do this, by the way, to go out to the house with a tape measure and a laser measure and a 100-foot tape and a sheet of graph paper and maybe a helper if they're lucky, and they measure the house, okay? And then if you're doing room by room loads, you got to measure the inside walls and rooms and everything like that. That can take hours to do. Here's a hot tip. If you're not familiar with this, I will put it in the. Let me make sure I'm sending it to everybody. I'm going to put this will make it worth your time to take this class all by itself. There is an app called QB Casa. It's a free app. Their website is www.cubi.casa. Okay, I just put it in the chat. Download that app onto your phone. It can be an Apple phone, it can be an Android phone. Go home, follow the instructions, and scan your house. You'll start in one corner and you'll point your phone at your baseboard where the floor and wall meet, and you'll just scan your entire house. Start in one corner, go all the way through your entire house until you get back to where you started. You upload that file, and the next day you'll get a floor plan of your house that looks like an architect drew it. And it's free. It is free. Okay. Try it. It's amazing. When I first discovered that, I was like, oh my gosh, we'll never have to go out to a house and measure it again. It's huge. All right. And so that's a big deal for existing homes. Now, most energy consultants, they have a set of plans to work with. Okay. But if you start doing load calculations, you might start getting a lot of contractors calling you and say, hey, I need a load calc on this house. They want their equipment or they want to switch to heat pumps. Okay. So now you start to get a business opportunity of just doing load calculations. All right. So QB Casa, it's awesome. How do they make money? Well, their target audience is realtors and home appraisers, so they have upsells. If you want your floor plan to show furniture, that's an extra $10. If you want your floor plan to show plumbing fixtures, that's an extra $5 or something. But a basic floor plan that just shows the walls of the house and the shape of the house is free. And that's all you need to do a load calculation. Now it won't show window sizes. It'll show window locations and window widths, but it won't show the height. So you do have to measure the heights, and you do have to measure like if there's vaulted ceilings and stuff like that. But still, it's so much better than the way we used to do it. Okay, so collecting information about the house. Once you have all the information, you plug that into a software program. Some software program, it's really tedious to do that. All right. So CBEC Res, for example, if you have a floor plan and you got to get the information from that floor plan into the software, you got to take out you may, if you're clever, you might have a way to do it as a PDF and do measurements, stuff like that. But back in the day, we used the good old, I can't believe mine's not within reach. The good old uh, tri-square, the architect's rulers. You know these guys, and you had to come out. You had to find the right scale, and you'd measure the walls. You type that in, and all that other stuff. The new software these days makes it so much easier. Okay, so you get it into the software. Then once it's in the software, you run your load calculations. Okay, then once you do your load calculations, you select your equipment to meet those loads. So that's manual S. And then once you know your equipment and you know how much airflow, then you design your ducts to that. Okay. So collect information about the house, and then it's just manual J, manual S, manual D. Okay. That's the full process. I think there's no reason in the world why every energy consultant couldn't do the first two parts of that easily and then learn to do manual S and manual D. Okay. All right. So the software that's out for HVAC design, RightSoft has been around for years and years. That's what I used almost my entire career. I started using RightSoft when it first came out in the early 90s. Okay. And then Elite came out sometimes later. Elite's almost a clone of RightSoft. All right. And then in the last 5 years, a new software comes out thanks to my son and me, Quick Model with energy gauge loads. So these are the three main manual J approved software that does manual J, manual S, and manual D. There's about 8 others that only do load calculations. But again, if you're going to do load calculations, I highly encourage you to at least provide a file that you can then do duct design on. Okay, and so any one of these three can do that. All right, so pick your software, whichever software you want to use. More power to you. Learn to use it and use it well. Okay. Now, what you're doing when you do a load calculation, the information that you actually need are the areas, and you do this for Title 24 calculations, right? You know all about wall areas and gross wall areas and net wall areas and windows and ceiling areas and partitions and all this other stuff. You guys are experts with these areas and stuff like that. It's the same exact stuff. The only difference is that we need it on a room by room basis. Okay. So instead of just one big ceiling, we need 1, 2, 3, 4, 5 ceilings for this really, really simple little house. Okay. Um, let's see. Question here. Sorry, I got because how critical are ceiling heights and volume? Actually, not that critical. I just did a load calculation on this new house the other day, and it had 10-foot first floor, 9-foot second floors, and then they called me back and said, "Oh, you know, I think we decided to go 10-foot second floor also." I go, "Oh, okay." So I just raised the floor a foot, and it had a teeny tiny impact on the loads. It had more impact on the heating loads than the cooling loads, but I was surprised how small it was. If you have a vaulted ceiling, a lot of people say, "Oh, vaulted ceilings, that's going to cause that room to be really hot." Is the vaulted ceilings? It's not the vault that caused the ceiling to be hot. It's the fact that they didn't do a good load calculation, and they probably didn't put enough air in that room. But if you think about it, you have a flat ceiling, and then you vault the ceiling. That adds a tiny little bit of extra surface area to the ceiling, but the main thing is the two triangles that it adds on either side. But that's it. That's not that big of a deal. It doesn't change window sizes and stuff like that. So it's not huge. It's not huge. Let me put it that way. Jenna is asking IES-V can't do it as a plugin. I'm not sure what that is. I'm sorry. I'm not sure what that IES-VE is. Is that the commercial software? Manual J is purely residential. Okay, Manual J is purely residential. So there you go. All right, so ceilings. On a room by room basis, you need to know the ceiling of each room. So it's interesting on a two-story house, all the upstairs floors, all upstairs rooms, those all have ceilings. The downstairs typically do not. And so you could have the exact same room, size room on the second floor and on the first floor, and the room on the second floor needs more air because it has that extra ceiling surface area. So that's why we do load calculations is to catch that kind of stuff. Walls, same thing, but it's tracked by room and by orientation because it's got windows in it typically. Doors, doors. I always try to brush off doors. If you, doors are a waste of time. If you look at the doors, are like 1% of the envelope load, which is like in the envelope load is like 60, 70%. So 1% is just doors are a waste of time. But anyways, do your doors. Floors, same thing. You need to know floors on a room by room basis. Okay. But if you use the right software that draws out the rooms and everything, it'll do that for you. It's not that much more work. All right. And then windows, of course, and of course, windows get extra complex because now we talk about orientation and shading and stuff like that. Oh, I thought I saw a question about shading. Oh, there was one. What do you do about shading obstructions not connected to the building? Manual J does not officially address that, but what I typically do is if I think a house is substantially shaded, you can either fake that by calling it an overhang of some sort, or if it's a tree or something like that, you can enter a shading coefficient, like a shade screen sort of thing, but it only on the windows. The solar gains on walls and stuff like that don't have that big of an impact, but you can fake it. And what I always tell people is if you're not sure, run your low calc, take a screen snip or write down the number, change something, run it again and see how big of an impact it makes. Okay. And what you'll find a lot of times, it doesn't make that much of an impact, but shading can. Shading on, especially on the west side of the house. If you've got a huge row of redwood trees that don't lose their leaves and they're always shading the sliding glass door on the left, I don't have any problem with throwing a little 0.6 shading coefficient on that window just to take that into account. But you need to be able to justify that. Okay. Let's see. Thank you. Thank you. Oh, a Scottish software. I'm not familiar with that, Jen. I would love to know more about that. So why would a first floor room not have a ceiling? Because there's a room above it. Let me clarify that it has a ceiling, but it's not an external, not an exterior surface. So we're talking about surfaces that heat will transfer through. So if you have a first floor room, the ceiling, if you drill a hole through the ceiling, you're going to go into the second floor. So it's theoretically it's the same temperature. It's an adiabatic surface, so there's no heat transfer through that. But on the second floor, you drill a hole through that ceiling, you come out in the attic. So there's a lot of heat gain and heat loss through that ceiling. That's what I meant. So good question. Okay. these are the surfaces that will conduct heat into and out of the house. All right. And you guys are experts at this if you're an energy consultant. This should sound familiar. All right. The only difference is instead of in we only care about these surfaces at 2 points in time when it's a certain temperature outside and a certain temperature in the summer and a certain temperature outside in the winter. All right. But for energy calcs, well, the software does all that for you anyway. So, but it's the same principle. You'll need to do this on a room by room basis if you want to size your ducts, and I highly, highly encourage you to do that because that's really valuable information. To know that this room needs a certain amount of airflow is really valuable information to someone who needs to do a duct design. Okay, and I've seen tiny rooms need an 8-inch, and I've seen in the same house big rooms need a 6-inch duct. So it's not about the size of the room, it's about the room's load. How much windows does it have? How much exterior surface area does it have? What direction those windows face? All that kind of stuff. Okay. All right. The goal is to accurately estimate conduction, convection, and radiation. All right. You need to do it for the winter. So all the heat's leaving the house in the winter, and you need to do it for the summer. All the heat is coming in the summertime. And the software does that for you. The trick is getting it into the software. All right. If you're designing a system for a new house, most of the information you have is in the plans and the compliance docs. Okay. Um, the the CF1R Perfo one's got all the information you need. It'll even tell you the kind of equipment that they want to install. Is it a heat pump? Is it a gas furnace? You know, is it mini split, ducted, blah, blah, blah. It's all there. We're kind of lucky in that respect. Other states, they have to go hunt that stuff down. Even for new construction, they have to go down and they have to hunt down what the ceiling insulation is going to be in a house. They have to hunt down the wall insulation. They have no idea what the infiltration of the house is going to be. In California, it's fairly safe to assume five ACH 50 in a house. Okay, um, and especially if they're doing QII, if they're taking credit for being a tied house, like 3 ACH 50, it's safe to put that number in the loads too, because they're going to test it to make sure that works. Same thing with duct leakage. It's very safe to assume 5% duct leakage in a new construction house because that's code. That's code. All right. And someone's going to come out and test it, presumably at a HERS rater. All right. So if you're designing a system for an existing house, you may have to go out and sketch the floor plans. Oh, there's Cubicasa. I knew it was somewhere in the slides. I just wanted to make sure you guys got it. Okay, it's a free phone app that creates an amazingly accurate floor plan. All right. Then that's all the what we call the geometry of the house. That's all the areas and stuff like that. Now you need to know what kind of surface, what's the R value, how much insulation. For new construction, that's all in the CF1R. For existing homes, you're gonna have to do a little bit of research. Okay. um, you know, and we have a system where we have an online survey that the homeowner can fill out. I can actually do a load calculation, a very reasonably accurate load calculation on a house without ever visiting the house. Okay. We have a website called DIYLoadCalcs.com, and it walks the homeowner through the process. And we basically help the homeowner do their own load calculations. So they use Cubicasa to scan it. They fill out an online questionnaire that talks about the age of the house. You know, you learn a lot by finding it on Google Earth too. Um, and you know how thick are the walls. They take pictures of the windows, of the corner of the window, so we can see if it's vinyl frame, dual pane, metal frame, whatever. Okay, and just from that remote information collection, we can do a very accurate load calculation, reasonably accurate load calculation. The one thing we can't measure is infiltration. Well, I'm getting ahead of my slides. I apologize. For existing homes, you'll need to determine these features. For new homes, the information is in the compliance documentation. You will need to make some engineering estimates about things like duct leakage and infiltration. For new construction in California, those numbers are safe. 5% leakage, 5 ACH 50 for infiltration. Those are pretty safe numbers to use. I have heard some uh, testing being done on new homes where even though they're meeting all the mandatory ceiling stuff, they're testing out a little bit higher than 5 ACH 50, but that's the fault of the builder. That's the fault of the builder. So if you want to assume a little bit higher leakage than that, check it out and see. Run it at 5 ACH 50, run it at 6 ACH 50, run it at 7, see if it makes a big difference or not. And then be able to justify that information. Remember, don't oversize just for the sake of oversizing. Whatever your assumptions are, make sure they are verified in the field if possible. So on an existing house, if you assume a certain infiltration, you probably should test the house. Okay. Now, what we do with those remote load calculations is we run the house as average leakiness, and then we tell the homeowner if your house is leakier than that, here's how it's going to affect the loads. If your house is tighter than that, luckily you, here's how it's going to affect your load calcs. Now it puts them in that mindset of, ooh, I have some control over this. You meaning I can make changes to my house and actually impact the size of equipment that needs to go in my house by making my house better? Wow, what a concept. Okay. So anyways, that's an important thing. Duct leakage, I mentioned all that. Okay. For altered systems, it's pretty safe to assume 10%. That's the new code now, and HERS Rater's going to come out and test it, unless it does that smoke test. I've done the best I can test. Infiltration can have a big impact on loads. Okay. For existing houses, it's a good idea to measure with a blower door. All right. But like I said, on the DIY load calcs that we do for homeowners, we give them a range. We say, here's what it is if the house is really tight. Here's what the house is really leaky. Here's what it is in the middle. And we let them decide, what they want to do about that. It is a very bad idea to do a load calc that assumes a very leaky house. Teach my manual JS&D classes, I like to tell contractors, don't design an HVAC system for a crappy house. Like, oh, what does that mean? Well, it means don't plug in a really bad leaky number to your load calculation and size the equipment to that. That doesn't make any sense. Fix the house. Fix the house. Do your load calc assuming the house should be as leaky as it should be, as it could be, without a ton of work. Okay. So now that puts contractors in the mentality of not just being an HVAC contractor, but a performance contractor. And that's what I encourage HVAC contractors to consider themselves: home performance contractors, not HVAC contractors. You've probably heard the expression, when you're a hammer, everything looks like a nail. All right. When you're an HVAC contractor, every problem looks like an HVAC problem with an HVAC solution. And you're going to approach it with an HVAC solution when it might not be an HVAC problem. It might be a house problem. It might be the house is much leakier than it should be. It might be that the house doesn't have enough ceiling insulation in it. Don't oversize equipment to compensate for that. Fix the house. Okay. Fix the house. So, anyways, sorry, I'm getting on my soapbox. Um, so collect the information about the house. Some of the things might require measurements. All right. Then you do your load calculations. You can do a block load. That's if you run a house in Energy Pro, for example, you just run a basic Title 24 compliance run in Energy Pro. It'll do a block load, and what that means is all the rooms are lumped together. It's one number for the entire house or zone. Okay, and you can size equipment based on that, but you don't know where that air needs to go. If it's a ductless system, who cares, right? If it's a ductless system, a block load is fine. All right, if it's ductless, but if you're doing ducts, you need to know where that air needs to go. So I recommend a room by room load calcs. Okay. Room by room load calculations are important for designing a distribution system. These help you distribute the heating and cooling correctly so that the house can be very comfortable, even though it's sensing the temperature at one teeny tiny point where the thermostat is located. There are load calculations for both winter and summer. We talked about that. Okay. Winter is the heat leaving the house. Summer is the heat coming in. Let's look at heating first. It's simpler. So a heating load calculation is the sum of all the BTU losses, convection, conduction, and radiation, that occur when it's a certain delta T outside. All right. So it's 68 inside, and let's say it's 28 outside. 68 inside, 28 outside. So you have a delta T of 40. That 40-degree delta T is what drives conduction through heat transfer through the walls. Remember UA delta T? Okay. And then infiltration leakage is also a delta T number. It's CFM times 1.08 times delta T or something like that. Okay. Um, for heating loads, we don't pay much attention to radiant losses. When you look at a house with an infrared camera on a really cold day and you see the orange glowing stuff, that's radiant losses, radiant heat loss. Okay. But it's very, very small on the heating load side. Okay. So we don't pay much attention to it. In the summer, however, radiant heat gain is huge because that's sunshine. That's heat coming through. Winter load calculations they happen at night. Okay, just realize that load calculation is done when it's a certain temperature, and that's going to be at night. The coldest time of day is at night, and so solar gains aren't there to help you heat the house. So there are no solar gains for heating loads. For cooling loads, however, it gets much more complicated because now, let's see if we know that. Um, it gets more complicated because now we have to worry about sunlight and windows and overhangs and shading and solar heat gain coefficients and all this other stuff. So cooling loads get quite a bit more complicated, um, and overhangs can have a big impact. Okay, overhangs are one of the most underappreciated energy features, in my opinion, um, and um, and then it depends on orientation of the house. So I hear that um, I hear that rule of thumb all the time: 500 square feet per ton, or if you're in a really hot climate, it might be 400 square feet per ton, or maybe out on the coast, it might be 600 square feet per ton. So they're looking at the size of the house and sizing the air conditioner based on the square footage of the house. And there is some correlation, but not good enough to design by. I have a sample house that I use in some of my classes, and I can take that house and I can rotate that house 90 degrees, just 90 degrees, and it goes from a 2.5 ton to a 3.5 ton, just by turning the house 90 degrees. I didn't change the square footage. The only thing that changed is the direction that the windows are pointing, and that alone can have a big impact on your summer cooling load. Okay, so it is important. You have to understand that stuff, and then of course overhangs matter which side of the house they're on. Okay. All right. So look at this very simple house. Okay. It's just a shoebox. It could be a little ADU. It's got a kitchen, living room, family. It's got a bedroom with a walk-in closet, a hall, and a bathroom. Okay. Notice that the kitchen and living room are the exact same size: 10 by 15, 10 by 15. Okay. Now the kitchen has a north facing window. Here's our north arrows facing to the left. Our kitchen has a north facing window. The living room family room has a west facing window and a door. Okay. How does that affect the cooling load? Well, it turns out that is going to need a larger duct than the living room family room. Most contractors would not take that into account. Okay. Emma's asking about internal inputs like cooking. Yes, that is something that gets entered when you do your room load calculations. You tell it which room is the kitchen, and then the kitchen will be assigned internal gains based on that only for the summer. Okay, in the winter they say no, all your stoves turned off in the wintertime. That's not gonna, because it's gonna help the heating load. But you also sprinkle people in here as well. Okay, for internal gains. So yes, internal gains is important. So yes, the kitchen, even though it has that internal gain, is going to end up needing more airflow. But a typical contractor would look at this and go, "Oh, they're the same size. I'm going to put the same size duct on them." And then what happens is in the afternoon, this living room roasts. Okay. Um, Now this tiny little house probably won't be that big of a deal. There's actually no wall in between these two, but you get the point. You get the point. Look at these. Look at these two bedrooms. One's got exact same surface area, exact same floor area, pretty much. But one's got a west-facing wall, one's got an east-facing wall. Manual J actually doesn't make that big of a distinction between east and west, strangely enough, um, because the sun BTUs come in the morning too, and they'll be in the house. But those sorts of things come into play. Those sorts of things definitely come into play. All right. Cooling loads and the subsequent sizing of the equipment is much more precise and evolved than heating loads. That's the equipment, as I mentioned, depends on design conditions. So the actual output, the capacity of an air conditioner, is not as easy to determine as a furnace. But now we're talking about heat pumps, and now heat pumps are more complicated to size certainly more complicated size than a furnace. Um, but so that's manual S. But again, you have to have a load calculation. You need a measurement before you can put a suit on the person. Okay. All right. Depending on the software, you must input all the surface information by either manually typing it in. That's like we do with CBAC. You measure it on the floor plans and you type it into the software. You measure the windows, you type it into the software. Um, man, RightSoft and Elite load calculations, you draw the shape of the rooms and you tell it the height and it'll do the math for you. And then in Quick Model, you build the house in 3D. You place these boxes, you scale the box to match the rooms, you build the house out of these boxes, and it does all the takeoffs for you. Okay. So, but the point is getting that information from the plans, the geometry of the house from the plans into the software. The software will then use that information to select the correct value for manual J. Well, you got to tell it the kind of walls too, and the kind of ceiling, the kind of floors, the kind of windows. And then it goes to manual J, says, okay, grab this number, boom, there's your heat transfer for that surface. Um, as you can imagine, this is a lot. There's a lot of surfaces to take care of, which is why you need good software. So that really, really, really simple house had 1, 2, 3, 4, 5 windows. Okay. And that really, really simple house had 9 walls. That's not too bad. That's manageable, 9 walls. But that was a really simple house. What if you have a house like this? Not super complicated. It's a 1,750 square foot ranch style single floor home. Okay. How many windows, how many walls is this house going to have? It's going to have 30 walls. There's 23 on the graph. It has 23 walls because look at the master bedroom alone has 3 walls. Okay. So it can get complicated. So that's why you need to use good software, use it correctly, and make sure you do a good job. Okay. Paul is asking a question. Does Quick Model allow input directly from 3D architectural model, Vectorworks, or AutoCAD? No, not at this time. It does not. You import a 2D floor plan and you build the house out of 3D boxes on top of that. Um, our target audience, to be honest, is smaller HVAC contractors. They are CAD phobic, if I could say that. Um, and so we actually sort of advertise the fact that you don't need CAD to use our software. Um, and it tracks walls and surfaces very differently than how a CAD drawing is drawn. But I will tell you, it builds the house in 3D very quickly that it's almost as fast as importing a CAD file for a pretty simple house. We like to say our software is more like Minecraft. If you ever heard of Minecraft, the video game Minecraft, our software is more like Minecraft than AutoCAD. So it goes really quick, and it's the appropriate level of precision, whereas CAD is probably CAD and Vector and SketchUp is way more precise than you actually need for a load calculation. So anyway, sorry, the short answer is no, we don't. Okay, so just to reiterate, um, load counts are simple. Equipment selection and duct design is where it gets more complicated. I really, 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 really encourage energy consultants to just start doing load calculations and just say, hey, here's a load calculation. And then if you also give them the file, like if you do it on RightSoft or Elite or Quick Model, give them that file. And if they use the same software, let them fine tune it. Let them then take that information and do the design of the ducts and stuff like that. So now that file has some value to it. You can sell that file to people. It requires basically the same exact inputs as an energy model. An annual energy simulation, like I say, is 8,760 load calculations. If it's an hourly simulation, I know some simulations are even smaller than hours. Most HVAC contractors are not doing load calculations. If you do the load calculation, you make it available to them, there's no excuse for them not to at least take it into consideration. And then if it turns out that the equipment's way oversized, you can say, hey, I did the load calc here and they had access to that. They should have done a better job. I really, really think we need to start holding HVAC contractors more accountable for their sizing. Uh, let's see, when is the new software number 6? Oh, new software will allow house model to be used for both energy model and load calculation. Come to the May 30th at 2 p.m. class for 3C Ren. We're beta testing it as we speak. We're beta testing it. What it is, we have Quick Model that'll do manual JS&D load calcs. We call that Quick Model with energy gauge loads. And then we have another version of Quick Model called Quick Model CBEC. And what it does is you build the house in 3D both of those two programs do it exactly the same way. It'll create a CBEC file that you can then open in CBEC Res and just hit run without making any changes. Okay, and it'll run it, and then it'll do your normal Title 24 just like you normally would using CBEC. But then that file can be opened in the other version of Quick Model to do your HVAC design. Okay, we're beta testing that right now as we speak. If you're curious about it, and if you know our good buddy Luke Morton, he's been helping us beta test it, and he's been helping us a lot. So, and also Nick Brown is on the KBEC board as well, and he and I are gonna teach a class on May 30th and show it to you. We'll show you how it works and kind of give energy consultants a workflow that they can help, because our goal honestly is to help you know, energy consultants. I'm on the board of directors of KBEC myself, and we really want there to be more business opportunities for energy consultants. And hey, they've got all this expertise. Let's pull them in and help them make contractors do a better job on their work. Okay, again, 2025 Energy Code will put a much bigger emphasis on proper sizing. If you read the new 45-day language that came out, the requirements to do a load calculation is much more obvious. It's always been there, and it's just the building departments that have not been enforcing it, unfortunately. And those that have, congratulations. There are a bunch out there. By the way, it's kind of interesting. The very first building department that I ever ran into that actually asked for a load calculation, and they did a lot more than just ask for a load calculation. They asked for a full mechanical plan for a new house. Guess which building department that was? The city of Las Vegas. The city of Las Vegas. And that's because back in the late 90s, early 2000s, they were building a lot of retirement communities. And for senior citizens, when it's 115 degrees outside, air conditioning is a health and safety issue. And so the city of Las Vegas wanted to make sure those houses were built with proper heating and cooling systems. So they required a stamped mechanical plan. But that was the very first building department. Now, I want to say that was like 1995 when I discovered that. And slowly more and more building departments, now some in California, quite a few in California now, are asking for designs and stuff like that. There's parts of the country, I hear New York, I hear Florida ask for load calculations. They're even farther ahead than us in California, so it's interesting. So we shall see. All right, that is it. I'm 6 minutes early, which is unusual for me. There's my email. If you have any questions about anything we talked about, feel free to drop me a line. Russ@coded-energy.com. And now it's Itzel's turn.
Thank you so much, Russ. I appreciate that. Um, Great session. Just a reminder that we have the Energy Code Coach service. I wanted to drop that link there. If you have any questions, we have great coaches that could answer those Title 24 questions for you all. Next slide, please. Just a little bit of what we have coming. If you have any questions about AIA or ICC learning units, please drop me an email. I'll also put it in the chat. Happy to answer any questions. Also, to your email coming will be the slides and the recording and a survey and some of our upcoming courses. I'll also drop, it's okay. Some of our upcoming courses, I'll drop our calendar in the chat as well. And with that being said, thank you again for a wonderful class, Russ. And yeah, we could stay a little bit more just in case folks have any more questions for you.
Yes, happy to stick around and answer questions. Thanks, everyone. Does Accurate any other org conduct trainings for Manual J? I do a lot of training for Manual J. I've done it once or twice for 3C Ren. I do it quite often for Sonoma County. I do it for SoCal Edison, and I do it for PG&E. And there's a lot of recorded training that we've done. I do a 3-part class for both PG&E and Edison. If you go to their training and if you search for 3D HVAC design, it should come up. It's 3 sessions, and I believe it's 2 hours each. So it's like 6-hour training. Yeah, I do a lot. And then ACCA, if you go to their website, they do some, and they have traveling instructors that do live training. I would love to do live training again. Most of what I do is online now, but I would love to get back into doing live classes. I think we're actually talking about doing one in what's the Edison Training Center in Tulare. Yeah, it's out there. Just search for it. There's tons of it out there. There's in our website. If you go to Quick Model, KWIK, Quick Model, go to our YouTube channel. We have training on there as well. Generic training, not specific to our software. Yep. Thanks, Paul.
Geçti. Trafoya kedi girmiştir diye. Ceryan kesildi ve oylar bir anda değişti. Bir taraftan bir tarafa geçti. Biz bu ülkede gıkımızı çıkarmadık. Onları hep toplum kabullendi maalesef. Biz kabullendikçe bunlar çıtayı yükselttiler. Daha sonra ne oldu? Bakanlar sabaha karşı oylar sayılırken sisteme girerken seçim kurullarına girdiler, baskın yaptılar. Bakın, girin bakın.
I muted him. I don't think he was talking to us.
I don't think so either.
Levent, if you were talking to us, I apologize for cutting you off, but I don't speak whatever language that was. I apologize. That was funny. All right. I think that's about it.
No more questions. Alrighty, well, have a great rest of your day, everybody. We'll see you soon. Bye.
Bye. Bye-bye.